model of machining, sometimes our assumption is that the cutting tool is rigid. Rigid means that this is the Young's modulus is almost infinity, right? Also I put these two very, very important diagrams here about orthogonal cutting. So here's a chip formation. So this is a right-hand cutting tool. This one will appear. This one will appear in our final midterm. So here is how to describe, how to label. This is the different. This is the parameters. And then we talk about here are the characteristics of this is the machining. So we have turning. So we have boring, drilling, milling, planing, heating, broaching, and sewing. So the turning, drilling, and milling, and these three the operations are most commonly used machining operations, machining manufacturing processes. So here is the commercial tolerances are given here also. Remember, turning, drilling, and milling. Okay, we will do several modeling also. The cutting tool, as I said, yes, this is Susie's question. Is the midterm going to be a PDF? And we email to you, or will it be on camera? So I'm going to send this one out, and at the same time, I'm going to post this one on the cameras. All right? So you will receive my email after the Wednesday's class. So, and here are the requirements for the cutting tool materials. And first, the tool, we know that the tool is subjected to very, very high temperature and very, very high contact stress and rubbering on workpiece surface, the flammable, and the effects of chip climbing up the workpiece of the tool. So this is the tool. Whenever and you think about the characteristics of the tool, and you need to put yourself in the shoes and thinking, what kind of conditions my tool will be encountering. Okay, so then you can just imagine. First, the hardness. The hardness is very, very important. Now, I want to emphasize is that this hardness, I want to say, particularly at a high elevated temperature. Okay, some materials they are very, very hard at the room temperature, but as the temperature goes up, the hardness goes down very, very rapidly. That is bad also. That material cannot be used. So here is at an elevated temperature we call hot hardness. Hot hardness means that, and what is the hardness when the temperature increases? Usually around the cutting temperature. If around the cutting temperature of the hardness of your tool is still very, very high, just at least slight decrease, that'll be okay. But if the hardness goes down very, very quickly, very, very substantially, that means this material is bad, it's not good and to be used for the tool. And so that the hardness and the strength of the tool are maintained as the temperature encountered in machining operation. And I will test your understanding of the hard hardening. What is a hard hardening? And even though this one will not appear in our midterm, but in the final I will ask you hard hardening. The second one is the toughness. Why with toughness is important. Whenever we see toughness means that the capacity of my component that component to absorb energy and before it fractures. Okay, so the impact forces on the tool in the interrupted cutting operations is probably the milling. Milling we have multiple teeth, and such as milling or turning a spline shaft do not chip or fracture the tool. So that means the toughness. And the toughness is the capacity of my material and to absorb energy before it fractures. So sometimes the material is very, very strong, but very, very brittle. If there is any impact, it breaks. So that's still bad, right? So this is still bad. So the third one is wear resistance, so that a acceptable tool life is retained before the tool is replaced or indexed. Index means that you need to change, and you automatically change from one to if this insert is worn out, and you can automatically change to using another insert. So this is wear resistant. The third, last one is the chemical stability or inertness with respect to workpiece material. So if the tool material is very, very chemically active, whenever this tool sees this is some workpiece material, if it is infinity, very chemical reactive, very, very chemical reactive, it's also bad. Okay? You know chemical reactive, right? Chemical reactive means that one substance, one matter A, and sees the matter B, and they will have chemical reaction, and then the third material will be generated. The third material, that means mechanical properties change, everything is changed. Right? So that means inertness, chemical stability, inertness. I don't want my tool to have this chemical reaction with any of this material I'm going to use my tool to cause. So this is very, very important. So that any adverse reactions that will contribute to tool wear are avoided or minimized. So we have these are four very, very important characteristics, requirements for the tool material. So here is the hardness of the commonly seen kind of tools. We have ceramics, carbides, cast, these alloys, these high-speed steel, is a carbon tool, the steels, and here is this scissor is the temperature, and in degree F, here is the hardness, HRA. And do you know what is HRA? I'm just curious. It's not the interview. Do you know what is HRC? Are you taking the mechanical engineering lab? Huh? Okay, and you are going to take a mechanical engineering lab. In the ME lab, we will do the hardness testing. Okay? So
Hot-rolled coil?
Huh?
Is it a hot-rolled coil?
Rockwell. H is hardness. R is Rockwell. 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 A is a skill A, skill B, skill C. Okay, for our ME lab, we use skill C. That's the reason. And the specimens, they are designated as HRC, then a number. Okay? So HRA means the Rockwell hardness in skill A. Skill A, skill B, skill C, it depends on what kind of load you are using. And you will know this one later. But I want you to know this is the basic knowledge. HRA, HRB, HRC. And Brinell is HB, is another one. It's Brinell, BRINELL. Brinell is called HB. That is another way to measure hardness. You can see. So if I ask you guys to tell me which one is the best one in terms of hardness, I will select this carbide or this ceramic. Do you agree? So you can see these are carbon tool steels, and even though and at a low temperature they have decent hardness, but as the temperature exceeds 800, see, this is exponentially dropping to very, very low one. So this is a bad one. Okay? This is bad one. We should not use this one. We should not use this one. Cast alloys, sometimes we use it because they are relatively cheaper, but ceramic and carbide are commonly used one. So these are tool materials and different tool materials we have. So here, this is the high-speed steel cast alloy. WC is the tungsten carbide, and W is the tungsten, right? Tungsten, right? So the traditional lead bulb, they are made of this tungsten. This is tungsten carbide, titanium carbide, ceramics, and cubic boron nitride. So this one is, so this is from earliest one to the latest one. The single crystal diamond, that's what definitely this is the most expensive, but the best one for the tool. But this is very, very expensive. Usually we do not use it for our case. Tungsten carbide will be great. Tungsten carbide, ceramic, that it will be great. Tungsten, this is the titanium carbide is also great. Sometimes we use this one because they are the cheap price, but tungsten carbide, ceramic, we use more. So this cubic boron, sometimes we use them also. But this one is the most expensive one. So they are the hardness, compressive stress, all this is the mechanical parameters are given here. So here is in approximate chronological order from the earliest one and to the latest one. First one, the carbon and medium alloy steel, carbon and medium alloy steel. At that time, at the very beginning of this is the Industrial Revolution. So this is very, very easy to find and also very cheap. And the high-speed steel is also great. This is a constant cobalt alloy, cobalt. And the fourth one is carbides. This is coated tool. And people found that the carbides, sometimes the tools cannot be used because they can be worn out very, very quickly. And then they introduced this coated tool. Coated tool means that I just induce this is the different layers of coatings on the carbide tool or other tools. Next one is aluminum-based ceramic. Is a ceramic coming to play. And next one, cubic boron nitride, and silicon nitride-based ceramic, the diamond and whisker reinforced and the nanocrystalline, the two materials. So diamond is the strongest one, is the hardest one. Hard is the natural tool. Silicon nitride based is also very great. So because it's ceramic come into play. This is a diamond, and from carbide here, people find that this is coated tools, different coatings. Remember, diamond is the hardest natural material. So, but the one thing is that diamond is very, very brittle. If it is impact, especially this one is bad for the milling or this drilling because it is multi-teeth. This is intermittent because intermittent turning, intermittent machining. Diamond tool is usually used for the turning. Right? Turning is continuous, so can minimize impact. So talk about the carbon and medium alloy. I'm sorry, this is the table here. Alloy, the steels. The carbon steels are the oldest of tool material and have used widely for drills, the tabs and broaches, and also reamers. And low alloy and medium alloy were developed later for similar applications. So because this sometimes this one cannot fulfill the purposes, so they have the new one. Low alloy and medium alloy, but with longer tool life. This is they had a tool life, longer tool life. As one is that this tool do not have sufficient hard hardness and wear resistance. The hard hardness means that as the temperature increases, their hardness increases substantially. That's bad. The use of these steels are limited to very, very low speed cutting operations. Why? Because low speed cutting operations, the cutting temperature is low. Right? So because the tool has bad hard hardness, so they can only use for this low speed cutting operation. Otherwise, if we use high speed cutting, the cutting temperature will be very, very high. And so it's because hardness is bad, and at a very, very high temperature, the hardness will be very, very low, and it can be very, very easy to be worn out for the tool. So this is the way usually this kind of tool can be used for low speed cutting operations only. And the next one is HSS, high speed high-speed the steel. This is very suitable for high positive reef angle tool. High positive means that high positive reef angle means that the tool is sharp, right? You still remember, right? So interrupted cars, this is milling or drilling, and for use on machine tools. This is mainly the CNC machine that are subjected to vibration and chatter because of their high toughness and resistance to fracture. So this is for HSS. Second one, the basic limitation is the relative low cutting speeds when compared with those of carbide tool. So this one is for when compared with the carbide tool. They not compare, but still this is the cutting speed for HSS is still higher than the previous low carbon skills. So M series molybdenum and T series is a tungsten, and they have this is M series and T series. They are developed based on this HSS. So people just use these different alloying elements. One is molybdenum, and another one is use tungsten. Tungsten is hard. The next one is the new material. This is relatively, I'm talking about in the order, the time order. So for the cast cobalt alloys, they have high hardening, HRC. This is what I just told you, right? The previous one we have for the diagram, we see HRA, and here is HRC. So this number, whenever you see HRC and around this number, that means the speed of the hardness is good, very good. The good wear resistance and maintain their hardness at elevated temperature. So that means the hot hardness is very good. So this is also known as the solid tools, and they are cast and ground into relatively simple tool shape. They are cast and ground. So they are sensitive to impact forces, consequently, and they are less suitable for interrupting the cutting operations, especially for the cutting. For the face, for the face milling, if the plane milling, the face milling is very, very big, one revolution, another revolution. So this is interrupted kind of operations. And they are used for special applications. They involve a deep, continuous roughing operation at relatively high. This is a feed rate and speed. So this is F is a feed rate and speed. So this is the custom cobalt alloy for the tool. The next one is a new one. New one is the carbides. And the carbides, they are known as the cemented or the sintered carbides. They were introduced to meet the challenge of higher machining speed and for higher the production rates. So this one, a carbide tool, is suitable for a high-speed machining. And they have high hardness over a wide range of T. And so this we just saw the diagram. And high elastic modulus E, and thermal conductivity and low thermal expansion. Also, the stiffness of machine tool is important for the carbide. Light feed, low cutting speed, along with the chatter, can be detrimental for this if you use the carbide tool. The plain carbide tool, uncoated carbide tool, and then you have tungsten carbide or titanium carbide tools. So this is a plain carbide tool, and means you don't have this anti-coating. But the people want to increase the wear resistance of the tool, and they have the tungsten carbide and also is a titanium carbide. But these are carbide tools. Here are the properties of tungsten carbide tool. It depends upon this is the cobalt content. So here is cobalt content, head weight, and here is where compressive and this is transverse rupture strength. The different values, compressive strength, hardness, and transverse rupture strength along with the wear. So you can see as the coolant content increases, the wear Mg is increasing. So this transverse rupture strength is increasing also, but hardness and compressive strength, and both of them are dropping as the cobalt content increasing. So then we talk about inserts. This insert, you know insert, right? If you have taken the machine shop and you know that here's a tool holder, and we just change the insert. This insert is a very tiny piece. So this is insert. So this is a tool holder. This is a clamp screw. This is a clamp. This is insert. And here is the seat. So you can just take this away, this insert. You can buy this insert and just buy this insert online. This is shank. And this is a longer pin here, and this is a seat. Here, this is a tool holder. I think you are very, very familiar with these tool holders, right? So my laser machining lab is downstairs. So when I go to my laser machining lab, I need to go to the machine shop first. I see a lot of these tool holders with these kind of things. So insert strength. So insert strength, you can see here is the round one. So here is the angle. Here is the angle, and here is the square, and here this is angle decreasing. And so this is 60 degree, and so this is 55 degree, and this is 35 degree. So this is relative edge strength and tendency for chipping and breaking of insert with various shapes and different shapes. The strength refer to that of the cutting edge shown by the indulged angles, included angles. So here, definitely this one is this is the wrong one, right? Increase the chipping and breaking. So this one definitely is the weakest because it's the sharpest one. This is increasing strength. This one is most the strongest one. So this picture shows the edge preparation for inserts to improve edge strength. So here, so this one is a negative with land and a horn. So this is negative with land without horn. So this negative horn is negative sharp. So this is a positive with horn is a positive sharp. So this increasing edge length. So you have done the homework state, homework 5, right? Homework 5 and different edge radius, and you will have different cutting performance. Okay? So this is edge preparation. How do you prepare the edge? So coated the tools. So coated tools, as name suggests, we have the tool insert, but for some reason, we want to coat this tool insert using some coating material. So usually, so this coated tool reduce the time required for machining and can improve the tool life by as much as 10 times that of the uncoated tool. So coating, that means, so there are some requirements about the coating material. The coatings should have the following general characteristics. First one, high hardness at elevated temperature. Right? This is very, very important. Otherwise, if the temperature goes up, and so this is the hardness of the coating material is low, and it will be worn out very, very quickly. Second one, chemical stability and endurance to the workpiece material. You cannot, this coating material cannot have chemical reaction with the workpiece. Low thermal conductivity. Why this one is important? Somebody tell me why low thermal conductivity is important.
Would your tool not get hot? That's easy.
Yeah. Okay. Right. So low thermal conductivity, I want to use the coating material to protect my tool. If this guy, the thermal conductivity is very, very high, all the heat comes into my tool insert. That's not good. The good bonding to the substrate. Substrate, that means good bonding to the tool, the tool, right? Otherwise, the debonding will be occurring. Little or no porosity. The porosity is also bad. So generally, in the thickness range of 2 to 10 micron, the coating are applied by the chemical vapor deposition. This is called CVD. Another one is a PVD. The PVD stands for physical vapor deposition. So the physics department, the SLUS physics department has this is the CVD. If you are interested, and I can just show you around, but I need to ask for permission from the physics department. Chemical vapor deposition. So this is the commonly used coating materials are titanium. This is the nitride, titanium carbide, titanium carbide nitride, ceramic coating, multi-phase coating, diamond coating, and other coating materials. So this is the titanium, aluminum nitride, chromium carbide, chromium is carbon. So this is commonly used the coating materials. The historical tool improvement. So here, so this is the years. This is for 1900 and to is to the 20,000. So this is 100 years. So, so this is machining time. Machining time that your tool can withstand. Here is the starting steel. Then there's a high-speed steel, the custom cobalt based alloy, cemented carbides, improve the carbide grades. And first coated grades is here. At this time, around 70. First the double coated, first the triple coated, and the functionality graded the triple coated. This is the material. So this is machining time, right? The relative time required to machine with various kind of tool materials with indication of year the tool material will be introduced. Within 1 century, machining time have been reduced by 2 orders of magnitude, 100 times, 100. So this is a coated tool. Let me show you. Here is our rig face. So here is our tool. So this is the titanium nitride coated. And here, this one is uncoated. This is the dotted line. This is a dotted line, dotted configuration, and shows the uncoated tool. So here is a titanium nitride coated, and this is a rig face. So here is the flank wear, guys. This is the flank wear from here to here, and for this uncoated, one. For this is coated is from here and to here. Did you see the difference, guys? So that means if you use coated material, coated tool, the tool flank wear is much larger, much smaller than that for the uncoated one, right? So if the flank wear is bigger, is much bigger, it is very, very bad. Why? Because you just change the configuration of your flank surface here, and if the flank surface is changed, and you so that your tool will rub the machine surface, will rub the machine surface. So know that the flank wear is lower for the coated tool for this one. So this picture shows the multi-phase coating on tungsten carbide substrate. So this is a carbide substrate, and we have different the coatings. The 3 alternating layers of aluminum oxide, 1, 2, 3. Okay, 1, 2, 3 is one pattern. 1, 2, 3. The second one. 1, 2, 3. 1, 2, 3. So this is another one. So this is 3. These are 3 alternating layers of aluminum oxide are separated by a very thin layer of titanium nitride. Titanium nitride here. So inserts with as many as 13 layers of coating have been made. The coating thickness are typically in the range of 2 to 10 micrometer. So this is give us an example of multi-phase coating. We have different coatings. So this is kind of extreme case. Okay, so usually we don't need to have so many coating, so many layers of coating for the tool. So then we talk about alumina-based. This is ceramics. So they are consist of the braid, the high purity aluminum oxide, and they have high abrasion resistance and hot hardness. So abrasion is the two guys. They are come to contact each other. The abrasion is abrasion resistance and hot hardness. The CBN, so cubic, the boron nitride, and the silicon nitride based ceramic, silicon nitride based. CBN is very hard next to the diamond. So SLN have high toughness, hard hardness, and this is the good thermal shock resistance. What is the shock thermal resistance? What is the shock thermal resistance? Thermal, right? Thermal is because of heat. Shock thermal resistance means that if the temperature changes substantially, this is my material will be okay. Otherwise, it's a shock, just like impact. Heat, very hot, very low, very hot, very cold. The thermal shock. Here are the properties of cutting tool materials. This is the strength and toughness. Here is the hot hardness and wear resistance. And based on this diagram, you can see this one is very hot hardness, but and wear resistance, but the strength and toughness is bad, right? For another extreme is HSS, and they have very high strength and toughness, but the hot hardness along with the wear resistance are very low. And for our case, and we just use we need to think about this trade-off. And we just get silicon nitride or ceramic. We don't want to go to one extreme, and we don't want to go to another extreme as well, right? Do you agree, guys? This is how when we select things, we always want to go in the middle and don't want to go any extremes. So here's a construction of polycrystalline, the CBN or diamond layer on a tungsten carbide insert. So here is a tungsten carbide insert. So this is the brace. Here is a carbide substrate. On it, we have polycrystalline CBN on or diamond layer. So other materials. The other materials is a diamond. Diamond is I told you, diamond is the hardest material, hardest natural material. Another one is a whisker. Whisker reinforced and the nanocrystalline tool material. Whisker means that this you have chopped this material. Chopped. This is the fibers. These chopped fibers into this matrix, and then thin it, and to get this crystal material. And they have very high fracture toughness, resistance to thermal shock, and cutting edge strength, and hot cutting edge strength. I mean, on this cutting edge, and also hot the hardness. This is about whisker